Okay, so consider the fraction 1 over 7, right? Seems like a pretty weird fraction, but if you write it out as a decimal, you get 0.142857. And these 6 numbers repeat forever. That's weird, right? Why would it be these 6 numbers? It gets even weirder. If you write 2 over 7, just multiply the whole thing by 2. Guess what you get? You get 0.285714. It is repeat. Sorry, I'm kind of messed up there. But 3 over 7, you get 0.428571 repeated. You notice something here? These are the same 6 numbers in the exact same order. It's like they're in a circle or something. Like, look, I can keep going. 4 over 7, 0.571428. Type it on a calculator. Just type it out on a calculator. Get out a calculator yourself, and you will find that these are the answers.
You know what's even weirder? It's not just 7. It's not just 7 that exhibits these traits. It's actually all of the prime numbers. All of the prime numbers exhibit this trait. It's so weird. The next number would be 11, but 11 kind of breaks this rule. I'm gonna address this later. See how 11 kind of breaks this rule. But I'm gonna address this later. If you skip 11, you get to 13. Look! 13. Same 6 numbers repeating. It's 2 sets of 6 numbers, actually. See, you have one set of 6 numbers here. And then this set comes up again here. And then it comes up again here. And the other set of 6 numbers, it comes up again here, here, and here. It's seemingly random. What's happening? If you keep going, you get to 17. You get to 17. 17, look. You have 16 repeating numbers that are just cycling over and over and over again. Weird, isn't it? And 19. This is the point where Python doesn't have enough decimals to keep up, but you can infer where these numbers will repeat by looking at all of these. You have 18 repeating decimals for every reciprocal of 19. That is so strange.
Of course, I can actually see a bit of a pattern in these prime numbers, or these prime fractions actually. For 7, let's start with 7 here. I'm gonna write out these numbers in a bit of a circle. 7. So this is a circle and it goes clockwise. So using a different color, I can start saying 1 over 7 starts here. 1 over 7 starts here. 2 over 7 starts here. 3 over 7 starts here. 4 over 7 starts here. 5 over 7 would start here. And 6 over 7 would start here. So you can see that 7 is structured in a way that it is basically 6 different permutations for 1 to 6. Right? Now, what's different about 13 from 7 is it's a little weirder. I'm gonna have to copy the numbers down. We have 12 numbers in total. That's kind of like 6 plus 6 for 1 to 12. I think we can explain 17 and 19 having 16 and 18 integers repeating over and over again. It's for the one for 17 minus 1 or 19 minus 1 number of fractions. So for 17, we would have 16 for 1 to 16. And for 19, we would have 18 for 1 to 18. But take a look at the pattern where these numbers actually start. So for both cases, they go clockwise. And I'm gonna read off of my computer screen for this. So for 1 over 13, we start at 0 here. And for 2 over 13, we actually start at this 1 here. 3 over 13, we start at this 2. We would start at the 8, and 12 we would start at the 9. I don't know if there's a pattern here yet. I've only just started studying this really. But I think there should be. I honestly think there should be. Alright, so I drew up the circles for 17 and 19. This took a bit of a while. And I don't know, my mind tells me that the next step is to connect the dots. Right, let's start with 7. So let me move this up here a bit. Alright, I'm gonna start with 7. So I'm gonna start at 1. I'm gonna start at 1, and I'm gonna connect to 2. So let's do this. Connect to 2, then I'm gonna connect to 3. Then I'm gonna connect to 4. Let's keep it I'm gonna connect to 4. I'm gonna connect to 5. Connect to 6. And then I'm gonna connect back to 1. Alright. I can see some symmetry in here. There's a triangle here, 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 here. But I don't know if that means anything. Let's try it for 13 now. So this is a little strange, because consecutive numbers are actually on different planes, I should say. So I'm thinking maybe we construct a 3-dimensional object using this. Okay, so I've reconfigured the 2 hexagons we got from the 13, and I guess we can draw a 3-dimensional cylinder of sorts? Not sure. Anyways. Then 11 to 12. And 12 goes back to 1. So I'm seeing a bit of symmetry here. It goes a bit like all over the place, but I'm seeing a bit of symmetry. You can see there's a crossover point, there's a bit of some doubling going on, and I feel like as a 3-dimensional object, if somebody can help me model this, this would be very good. And I'm gonna see if I can get a planar view of this. Okay, so I've connected all of these numbers in consecutive order. If you follow the path of these red lines, you're going to get the sequence of starting numbers as listed here. You can see the first column of numbers. You're gonna get the sequence of starting numbers, and I'm beginning to see some weird patterns here, and they're mostly bisymmetrical. So like you can kind of well, not bisymmetrical, like radially symmetrical. You can kind of rotate these 180 degrees, and I think they would match up if they were better drawn. This one especially, you can see this one is clearly radially symmetrical. So yeah, these are some weird patterns that I've been seeing.
And yes, I actually think it keeps going. See, here's 23. This looks familiar, doesn't it? And keep going. And we get to 29. See, 0344, 0344, 0344. There's another set here. And then you have many different sets, but it's just the same numbers repeating over and over again. And then you get to 31. Again, 31 is the same numbers repeating. It just keeps going. There's no way this is a coincidence. It just keeps going. Look, 37. 37. Look at that. Strange, isn't it? 37's even weirder. It kind of breaks the rules, but in a very strange way. You have these different 3-digit numbers with 37. And then 41. 41. You're gonna see it's 6 numbers repeating again. Different sets of 6 numbers repeating. So like, what's going on?